Our first session for the day begins with someone who truly shaped the foundation of modern deep learning. Razvan Pascanu is a renowned researcher at Google DeepMind, whose work has significantly influenced the way we understand and build intelligent systems today. Before joining DeepMind, Razvan completed his PhD at the University of Montreal, where he was part of the pioneering community that laid the groundwork for what we now call modern AI. He was one of the main contributors to Tino, the very first deep learning library in Python back in 2010, long before frameworks like TensorFlow or PyTorch even existed. Tino was where many of today's core ideas in neural networks were first tested and brought to life. And here's a fun story that perfectly captures the spirit of this field. Back in 2014, while still at the University of Montreal, a group of younger researchers were celebrating Razvan's PhD at a local bar called Les Trois Brasseurs. During that night, Ian Goodfellow, who was also part of the group, came up with an idea that would soon change AI forever: generative adversarial networks, or GANs. In the acknowledgement of the original GAN paper, Ian even tagged Les Trois Brasseurs for stimulating their creativity. So, if that's not the proof that great ideas come from a great company, I don't know what is. Please join me in welcoming Razvan Pascanu with his talk, Introduction to Deep Learning.
Thank you. Oh, okay, perfect. Cool. Thank you so much for having me here. Thank you for the kind words. I have to say I was against the idea. I didn't like GANs in the beginning. So that was one big mistake I did at that point in time. But it really did not make sense. At least after a few beers, it made no sense. Cool. So I'm gonna do an intro to deep learning. So I definitely have more slides than time. So the plan is not to finish the slides. So if you have questions, feel free to interrupt me, and we'll just go and see how far we get. I actually had a slide on EML, but we can jump that because Petar covers it quite well. But just keep an eye on EML, the full summer school. So we're probably going to announce it soon, hopefully in the next few months, maybe less than that, hopefully, and try to join. And yeah, I wanted to start to talk about deep learning. And before that, yeah, just a bit of like, starting from very high level, and then we'll quickly go into more technical details. So what is deep learning? And for me, at least, deep learning is something quite specific. So, you have the whole field of AI, and then there somewhere there inside you have machine learning. And some people are kind of saying that, ML equals AI equals deep learning. It's not really true. In my mind, they're very different things. And deep learning, it's a very specific choice of architectures that you use, and very specific choice of learning algorithms. We're going to talk a little bit about it. And if we have time towards the end, we're also potentially going to talk what's wrong with these particular choices. And that's why they might not cover everything. So just to have some grounding and start somewhere. So what is all this field about? So the simplest way to build intuition, and probably all of you guys already know this, but bear with me, is to start with supervised learning, where you're trying to think about classification. So the whole point is you have some data and you have some labels, and you want to have a way of assigning labels to data, right? So that's the whole game. And the question is how to do this. And one way to view the space and the partition of choices that you have is this through this idea of you have sort of parametric choices and non-parametric choices. So what you're doing is you're looking for this good predictor, which is a function h that goes from the data to the label. And you have two choices. You can have these functions that basically work on a set of training examples. So this would be the non-parametric case, right? So you directly work with your training examples, and you use this to label new data. And a simple example of that would be k-nearest neighbor, where what you're doing is whenever you get a new data point, you look in your training set, see which is the closest point to that one, and then you reuse the label. You say, okay, it has the same label as this guy because they're very similar. But another option is parametric models. And in parametric models, what you do, you're introducing new parameters, so introducing theta, and you're saying my function, instead of going from x to y, is actually going from theta and x to y. And then what theta is doing is basically summarizing your training set. So I think a good way to think about parametric models is that implicitly what parametric models need to do is they need to compress your training set into some parameters and then use this sort of compressed representation of your training set to help you make decisions. And as an example is a linear model, right? That would use a hyperplane or a line, and you'll say, okay, whatever is above the line is one class, whatever is below is something else. And then I guess sort of going back of what deep learning is, so just in generally, like when you're talking about this, like what you have is you have the function that you pick, the family of functions that you pick, so the parameterization that you have. So how does this analytical function look like? And this is what we typically call the architecture. And then you have a learning process, right? And the learning process, what it does is it's trying to find this theta star, which is the compressed version of your training set. And the whole point is that once you have this theta star, h of theta star, and some any new data point will give you the correct label, right? So these are the two elements. So when we're talking about machine learning, people talk a lot about architectures. A lot of research happens in the architecture, which is how you pick this family of function h, but there's also the learning process. And these are the two components that make things work. You typically have two things that you can worry about. One is my choice of parametric models H the correct one? So is it expressive enough to represent whatever I'm looking for? So this is usually work, this is like expressivity focused work. Or there's the learnability part. So like, can I actually find this theta star? And these are like the two main questions that you're fighting with when you're doing machine learning, right? Whenever you're defining a new architecture, you worry about, is this architecture expressive enough for the kind of data I want to apply it to? And then does this architecture allow me to learn? Like, will I have learnability issues? Would I have optimization issues when I'm trying to apply this function? And for deep learning, like I was saying before, like H is something quite special. It's a special family. It's neural networks. So, like if it's deep learning, then it has to be neural networks, and they should technically be deep. And then the learnability, like the learning process, is usually gradient based. So let's first look at the choice of H and how you navigate this. So the simplest thing that you can do is to pick a linear model. So in a linear model, H will look something like W times X. And this is kind of quite simple. What is the nice thing about linear model is that now you can do math. And like even today, a lot of times when we want to understand neural networks, we revert back to linear models. We linearize them in some way, or we're looking at like deep linear variants of the architecture we're using, right? So it's a very straightforward, and it's also kind of easy to interpret. So the way you'd understand the linear model is if you have this data in some space, you use hyperplanes to separate that space into regions, and then the labels are assigned to those regions. And then you can easily tell if a data point is part of a region or not. But the model is limited. So like, for example, this is the standard, the 2 moons data set. If you have 2 moons, there's no line that you can figure out of how to, how do you draw this line so that you separate the red from the blue? There's no way, right? And this is because the decision boundary is not linear. So then the question is like, what do you do next? So one thing that you can do is you can project the data into a different space where things become magically, or not that magically, but they become linearly separable. And just to give you an intuition, like for example, if we have data which is like 2 concentric circles, if we have this projection that instead of looking at the points in the 2D plane, we're just looking at the radius, then it's very easy to separate the 2 circles, right? Because like once I'm converting x1, x2 to x1 squared plus x2 squared, you have blue on the side, red on the side. And then it's very easy to do a line to separate them. So there is this idea that generally the way you would solve a nonlinear problem is to construct sort of this projection that would allow you then to use a linear classifier on top of it to do things. And to a certain extent, this is how neural networks work as well. But then the question is, where do you get sort of this nonlinear basis? Like, where do you get this projection that would allow you to separate things? And there's lots of literature on that. Like you have random projections, like we had echo state networks, which is sort of random recurrent neural networks that would do this. You have all kinds of kernels, but the problem with all of these methods is that you have to hand engineer the projection. And if you don't know anything about the data, like if you want to separate cat from dogs, it's really hard to say, how should I build a projection that separates cats and dogs in the data, right? So So what deep learning or a lot of machine learning is about is, okay, how we move forward, like we know how to deal with the linear classifier on top, but how do we move on and build this projection, learn this projection from data as well, so that we don't have to hand engineer it, and then therefore it has to work well. And one way to do this is to rely on neural networks, and this seems to be the thing that works really well nowadays and what everyone is using. And neural networks really were developed from a computational neuroscience, from a neuroscience kind of perspective, where the idea was, well, the brain does this somehow, so let's try to do it the same way as the brain does it. And the way the brain does it is through neurons, like you have sort of these very complicated neuron circuits, and we can try to mimic them. And neural networks are basically a super drastic simplification of what we understand about the neurons, right? They convert a neuron to a linear projection with some nonlinear activation, because each neuron has some nonlinearity in the way it works. And then another big inspiration from neuroscience that came into neural networks, particularly in terms of how the visual stream works in the brain, is the typical understanding of the visual stream. And as far as I'm no neuroscientist, so if there are neuroscientists in the room and they disagree with what I'm saying, you probably are right. But the early understanding in neuroscience was that the visual stream is quite hierarchical, right? And you have sort of this V1, V2, V4, IT kind of pipeline and how information is being processed. And this would create more and more abstract representations of your data that would, at the end, you'd be able to reason about. And this was the basic intuition of why, sort of in the early days, a lot of folks were pushing towards this sort of deep architectures, right? Because the whole intuition was that you need depth because you need to have this level of abstraction. You need to build representations that are more and more powerful. And it seems that the way you do this is by stacking things together. And this are slowly abstracting away from your initial signal to things like objects, faces, shapes, and so forth. So this was what was, I guess, in the 80s dominating the space. But of course, these analogies with biology can go so far. There's lots of issues. The neurons actually are quite complex. We don't really fully understand how it works. The visual stream is not exactly like that. It has a lot of feedback connection, and we don't actually understand how it works there either. So it's potentially not just a simple hierarchy. So it's better to switch to some math and try to understand why neural networks work more from a mathematical point of view. And potentially the easiest way to do that is to work with ReLU, which I think is still extremely popular. Maybe people now have been used to sort of slight variations of ReLU and so forth, but I still think understanding ReLU would probably help you understand most, if not all, activation functions that are using today. And ReLU is quite nice because it's a very simple activation function. It simply says if x is positive, return x. If x is negative, return 0. Right? That's sort of the nonlinearity. And the reason why ReLU is useful is because you can, I don't think we have time, but with pen and paper, if you look at these things, what it does, it basically converts your linear decision boundary into a piecewise linear decision boundary. So every time you have sort of a ReLU switching on or off, you have this points where you basically can change the slope of your decision boundary, right? So so each hidden unit creates one of these points. So it just basically enables you to deal with any nonlinear decision boundary. So that's a nice thing about, and that's one way you can think about neural networks, right? Particularly ReLU neural networks, there are these piecewise linear decision boundaries, and the intuition is if you have enough linear pieces and you can arrange them any way you want, then basically you can represent anything you want. And you can formalize this. The original papers from Chabenko and Hornick, I'm probably messing up their names, and so forth, they weren't necessarily about ReLU. ReLU came a bit further. People used to use sigmoids, but you can push sort of the same universal approximator theorems for ReLU as well. And all of this works. What I typically tell you is if in some limit, and that limit assures that you have enough linear pieces to play with, A single hidden layer model, which is all you need to create sort of these piecewise linear functions, can approximate any function. And I think intuitively that has to be very clear, right? Like if you give me any curve, I can use these linear pieces and arrange it. And this is a purely expressivity argument. It doesn't say anything about will I be able to find this particular piecewise linear decision boundary. Actually, that turns out to be quite hard. But there's nothing about there. And this is a result in the limit, right? So it says if I have sufficiently large, infinitely large model, then things would work. But this was enough to get a lot of folks excited. Even though if you think about it and if you look at how things work out in practice, I don't think this theorem is saying anything useful in the sense that the reason we use neural networks has nothing to do with this theorem, but it was enough to create a lot of excitement in the field and to keep the field alive in sort of the early days of the field. And then one natural question that you have, because this is sort of very important for deep learning, is why do we need the deep in deep learning, right? And early on, we did not have the deep, right? In the 80s and 90s, we had neural networks, and neural networks were one hidden layer usually. And the question is, yeah, from the universal theorem, like we can use one hidden layer and represent anything we want. What do we need the extra layers? I'm not going to do a quiz because I think I don't have the time. But I'm going to try to jump into the results. So there's something to gain, and people have been thinking about this. And the expectation is with deep, you gain something in expressivity, and that's sort of how a lot of these arguments usually work. So for ReLU, like it's really easy to construct the argument. It's actually easy enough that you can do it on board, and I would do that, but not in this instance because I don't have the time. But it's actually quite nice proofs that you can. They're pure geometric, so you can draw them. So it's pretty cool. But what you can ask for yourself is, okay, if I have a ReLU network and it's a piecewise linear function, one thing that I can look at is count the number of linear pieces. And one thing you can ask is, for a single hidden layer, if I have n neurons, what is the maximum number of linear pieces that I have? This turns out to be a widely known problem in geometry. So it's about arrangements of hyperplanes in the space, and there's a theorem from Zalewski, if I'm pronouncing the name correctly, from 75, that gives you the formula. This is the maximum number of linear regions that you would get if you have n units. And then the question is, what happens if I have multiple layers, right? How does this change? Can I extend Zalewski theorem for like a deep architecture? And that turns out to be a bit more tricky, so you can't really extend it, as in you can bound it, but you can provide like a lower, you can provide like the maximum number of regions you can have, but it's not as tight and nicely as Zalewski's theorem. But like just to give you the hint of how this works, in how the Zalewski's theorem works is by induction, and all you have to use is the fact that two lines, they can intersect in only one point. And you build on that, right? You can start with just two lines. Okay, they can only intersect in one point. That's how many regions they get. I add the third line that can only intersect the existing lines in one point, and then you can count how many regions they are. When you move to a deep architecture, the funny thing is, if I'm looking at a hidden unit on the second layer, that is already a piecewise linear function, right? So now what I'm intersecting is not lines, but piecewise linear functions. And then the question is, in how many points can two piecewise linear functions intersect? And the answer is in as many as you want, right? And then so the whole work then becomes, how can I construct these piecewise linear functions so that they intersect as often as possible? And if you look at these papers, it turns out, so there's a paper by Guido Montefar and so forth, it turns out that you can make them intersect often enough that you actually get exponentially more linear pieces. And what's funny about this and what I liked about this, so this is old work, maybe not as relevant now, but it really looks like, going through it and going through this exercise of doing the proof yourself, you can see that the way neural network works is almost like origami. So what it does, it takes the space, like if we are in 2D space, it makes it a bit easier. And it's almost like you're folding the space on top of each other. So every time you're adding a new layer, you're basically folding the space somehow. And the whole point is, if I fold the space many times, and then I draw like a simple decision boundary in the folded space, when I unfold it, this decision boundary gets reflected according to how I fold it and becomes a very complicated object. And that's sort of how neural networks tend to work, right? So there's this, it's not exactly origami, and if there's any mathematicians in the room, they can, again, because there's some weird stuff where you can map an entire region of the space to a point and things like that, which you can't do in origami. So it's not mathematically exactly the same thing, because apparently origami is an actual field in mathematics where people do math on this stuff, but it does feel like that a lot. So you can really have this intuition of what you're doing, you're folding the space. And this tells you something about the decision boundaries that you get from a deep neural network. And this is sort of just random stuff that I draw, but one thing that you realize when you do these things is that they're highly symmetrical, because the way you construct them is through this folding. So they have to have a lot of symmetries in them. And yeah, I mean, again, these are questions, but I'm going to answer them for you. So then the question is this the reason why deep networks work, right? So in the early days, this is what people were saying: deep network works because they're somehow exponentially more expressive, and there are different variants of this proof. This is the linear regions versions. There's things with sigmoids and so on that are more in the probabilistic space and whatnot. But all of them define some quantity that they say this quantity measures the expressivity of my model, and they show that with depth, that quantity explodes. And they say, well, we want to use deep networks because they're exponentially more expressive than shallow ones. But the funny thing is, you can start quantifying these numbers. Like for the linear regions, you can, right? You can actually compute that number. And what you can see is that number explodes for shallow models as well. I mean, it explodes a lot more for deep ones, but you're working with the kind of numbers that I mean, personally, I feel like they have no impact. Like, I don't think that is the bottleneck in learning, in learning these things. And you can tell that because, well, neural networks are not the only family of functions that can be this expressive, right? We can, using polynomials, we can also construct other things that technically match the level of expressivity if we only care about that of neural networks. But when you train these architectures, they don't work as well. So there is something else going on in there. And I think the thing that is more important than the number of regions is the symmetries that you introduce. And this is sort of the inductive bias of a neural network. And this is something that we don't know how to characterize mathematically. Like, we don't actually know how to describe the symmetries that are being built. But the reason I believe that neural networks work as well as they do is not because they're expressive, is because they have these very strong inductive biases. And here, this inductive bias is reflected through the symmetries that they build. Yeah, they have a lot of other pathologies. So, like, one question, for example, is how does a neural network behave as you go to infinity? I don't know if does anyone has a hunch by just looking at this picture? Do you have a sense of what will happen as I approach infinity? Okay, I'll just jump to the answer. So the answer is, like, if you look at this previous stuff, you realize that the number of linear regions is finite. So the issue is, as you go to infinity, you're going to be stuck on a single linear region. So the neural network actually starts behaving as a linear function. So neural networks will always diverge in their behavior as they approach infinity. And I think this is true for sigmoid and tanh and all the other. It's not the same proof or the same reasoning, but basically, yeah, if we think of a neural, like, you can use this to argue, oh, can an LLM add any two numbers? Well, no, because as I get close to infinity, things become shady. So, like, as I get close to infinity, like, they're not behaving in interesting ways anymore. And that's just because of how they're parameterized and how they work, right? So they usually have a region in the input space where they have very interesting behaviors, and then their behavior degenerates to something a lot simpler as you get close to infinity, which is not as interesting anymore. So the reason we have deep networks is not their expressivity, even though most work is like that. But what I think is happening is because of the inductive bias that they build. So the issue is we don't always know how to express this. So there's been works taking, again, a lot of inspiration from neuroscience that are looking at sort of what happens to the latent space as you go deeper in the network. And I don't know if you guys remember, this used to be the craze in the early 2000s, try to do this kind of plots on the left. So you plot the filter of your convnets and you show that, oh, the first layer discovers Gabors, and then, I'm starting to see noses and eyes on the layer above, and then parts of faces, and, this is what my neural network is doing. I think these kind of intuitions are exploited quite a bit in sort of interpretability work on neural networks, where there is this expectations that neurons have a particular behavior, and you can usually semantically identify that, and you can use this kind of saliency map strategy, so basically looking at sensitivity analysis to understand what the neural is doing. But of course, I think one needs to be careful, right? So I think these things are very useful as intuitions, but these are not math. These are more like empirical visualizations and understandings of the model. But we know that, like I think that the bit that I always worry about, particularly in interpretability work, is when people start assigning semantics to units, they start believing in that semantics. And then they kind of reframe the whole neural network in that sense. It's like, oh, I have this neuron that detects if the grandma is in the image, and I have this neuron that detects this. And then this is sort of what the model is doing. But the issue is, with anything, you can always like break it, right? So the neural networks are so flexible, and because you have sort of this space, you can always make them do what you want. So, you know that the typical adversarial examples where you can take any model and fool and make them, detect, say that the panda is something different. There's also been works where what they're trying to do is not to break the classification. So you want, whatever, these things to be classified as a llama, and it's still classified as a llama, but you want to fool the model to make it classified as a llama for the wrong reasons. So you can even manipulate the image in such a way that the model still predicts it's a llama, but by looking at the background, not by looking at the llama. So you don't, it's not just about the output. You can basically break the behavior of your internal features while doing whatever you want with the output, right? Either still predicting okay or not. And in some sense, at least this would be my reading, this is what today we call hallucinations. When we're talking about how the LLMs are hallucinating, obviously they hallucinate is because of this. And this is something that's, again, inherent in the architecture. Like, it's not something that is going to go away in any meaningful way. So you can mitigate it. You can say, like, okay, I don't want to have hallucination within this epsilon ball or something like that, because you can kind of control the behavior in some finite region of the space. But if you allow yourself to say, I want this to happen over the entire domain, all possible inputs that a neural network has, I think there's no paper for this, but I think you can easily, or potentially not that easily, but you can do it. You can write a paper that proves that that's impossible. Like, just by the shape and the way the neural networks are framed, hallucination is not something that you can remove. It's not something that's never going to happen. And these adversarial examples is not something that they're going to go away. You can control them, but in some way, there's always going to be some point in the space where you can go where things become bad. And yeah, there is this nice paper now. I'm not going to insist a lot on it, but it's a nice position paper from a few folks from DeepMind, like Csaba and Andras and others, where they're basically arguing that for some of this thing, the issue is not even the parameterization. I think, and this is kind of funny coming from someone like Csaba, who's been working on learning theory for a long time, but he's blaming statistical learning. So his point is that as long as you use statistical learning theory to train your model, so basically you do the normal thing, you're never going to be able to learn certain things. And you need to switch to something that they call exact learning. So it's kind of nice to see these kind of things. Obviously, as anything, you need to take it a bit of pinch of salt, right? This is not saying that you shouldn't use these models or whatnot to learn these things. It's just saying you need to be careful. That there is some limit in which you cannot go over, right? There's some things that never can be improved. Okay, I hope I'm not. Okay, so we talked a lot about expressivity and how we ended up with deep networks and how we build them, and then sort of the interpretation between them. I wanted to quickly switch about learnability. How do you learn these things, and how do you optimize and so forth? And this slide is only meant to make a differentiation between optimization and generalization or learning. So when you have your model, you have some training data and you have some labels for that training data. So one question that you can ask is, how is my model behaving on the training data? And that's something you can measure very easily. That's something you can control, and that's the optimization part, right? And you can always find a theta star such that you can get very good performance on the training set. But the tricky part with machine learning is that you don't actually care about the training set. You already have it. Like, no one is going to ask you to label the training set. Or maybe nowadays they are because they don't know what your training set is. But generally speaking, they shouldn't. They should only ask you about new stuff, not the stuff that they already given to you. So then what you care about is how the model is going to behave on data that I've never seen. And that's a little bit trickier because the training set doesn't necessarily tell you about that. And the way you bridge this gap, and that's sort of what the statistical learning does, is by just assuming that this data is coming from the same distribution. And then you can use this assumption and push it through and get that these two things are kind of correlated. But before that, I wanted to start with just optimization. So like, just say we want to just minimize the training set. How do you do that? So the issue with a neural network is that it's not a linear function anymore, right? It's a nonlinear, which means that it can look any way you want. So I draw here like a random function. And the question is, how do you find the minima of a function like this? And obviously, you can't find it, not in closed form, right? There's no way of knowing where the minima is. So what gradient descent does, it creates this iterative algorithm where I'm just going to explain like this because I find it quite intuitive, and I feel like a lot of people don't think of gradient descent this way. So what you're actually doing is you don't know how to solve the nonlinear function. So what you're doing is you're linearizing the function, right? So you say, well, I have no idea how to solve this, but if I approximate my nonlinear function by a Taylor expansion, I get sort of a linear approximation of it, and this is the red dotted line. And then you can say, well, I know how to optimize this. This is easy. The issue is that the minimum of this red line usually will be somewhere at infinity or minus infinity, depending on the slope of the line, right? And I'm pretty sure that that's not where the minima of the nonlinear thing is, right? So the minima of the red line is definitely not the same. And the reason for that is as I move away from where I started, from theta, the approximation starts to break down. And I know that if I go to infinity, this approximation has nothing to do with my original function. So then what you do is you add a trust region, right? You build this, find the minimum of the red line, but stay within this pink circle, because I believe that in this pink circle, the two functions are quite similar. So if it's small for the red line, it should be small for the nonlinear function as well. So you write this as a constraint optimization where you say, I want to minimize this linear function with a constraint where my change in theta cannot be larger than epsilon. You use Lagrange multiplier, and do I have the math? No, I removed the math because it was too much. But it's really nice when you just write this down, you actually just get gradient descent. So you can think of gradient descent as exactly this, is you always take a linearization of your model, you're trying to solve that, and you're just saying, I'm not allowing myself to move too fast. And how much you move is the learning rate. So the learning rate somehow implicitly decides this sort of trust region that you allow yourself to move in. Okay, so this is going to be the algorithm. So this is how we're going to do things, right? We're going to have this iterative process where we always linearize the model, take a little step, and keep going. And to do this, one thing that we need is to compute the gradient. And how do you compute the gradient? And the way we do it in neural networks is we start from the output and you apply the chain rule, right? And you compute the partial, or you can compute the Jacobians of each layers and stitch them together with multiplication. This leads to the famous backprop algorithm. And at some point there was a controversy with Jorgen and others arguing that this is just a chain rule from the 1700s. So what is the difference between the chain rule and backprop? Because they do look like the same, right? So why is backprop something and it's not just the chain rule? Does anyone know? So the trick is that the problem that we had in the 80s when this algorithm was introduced by Jeff Hinton wasn't that we didn't know how to do the chain rule. We knew the formula for the gradient. The problem is, how do we do this efficiently? So the question is, particularly back then when computers weren't what they were today, is how do I compute this thing with as little flops as possible? And basically there's the main differentiation between backprop and chain rule. So the point of backprop is that you start from the top, you don't start from the middle, you don't start from the bottom, or wherever you want. You start from the top, and because the output is the loss, it's a scalar, the dl on dy is a vector, and then you end up with a bunch of vector matrix multiplications. So then the amount of flops that you need to do is minimized, and the amount of memory that you need. If you start from the bottom, you start with matrices, and you have matrices throughout until you get to the top, where you kind of project that back to a vector. So the amount of compute that you end up doing is considerably much more. So this is kind of the main difference, right? So this is the key in backprop. I mean, anyway, I don't know how important this is. Like, no one cares anymore. Everyone just use whatever library they have, and they call tfgrad and whatnot. And but there is a reason. I just wanted to kind of answer to that tweet. It's not that it was nothing. It's the most efficient way of computing gradients. And like, if you would go to recurrent neural networks, and maybe I'll get to talk about those, you know, you have backprop through time, which is just backprop applied to a recurrent neural network. And this is by far the most efficient way you can compute the gradients. You have a lot of other algorithms that are interesting for many other reasons, like RTRL and so forth. And those are just doing the chain rule differently. The other thing I wanted to say is, when we think about optimization, a lot of people do that, but depending on backgrounds, a lot of people, when they come into it, they're saying, I have this function, I'm going to do the gradient descent, and I'm analyzing it, right? And it's just a function, and I don't care much more about it than that. It's just about the gradients. But actually taking into account the structure is quite helpful, because it turns out that one of the best tools that you have to debug an architecture is to understand how signal propagates and how gradients propagates in the architecture. And a lot of early works were basically just doing that, right? So your question was, I have some error signal above. What happens with this error signal as it goes through the architecture? And that basically is just like, what are these Jacobians going to do to my signal? Are they going to make it zero? Are they going to blow it up? What's going on there? Almost all work on initialization is about that. So like, you know, Xavier Glorot and Joshua paper, Hamminghe, you know, initialization and all of this stuff, they're basically just asking the question, in expectation, what's going to happen with some signal if I feed it through the network? And how do I initialize my model such that the signal does not disappear or blow up? And this is still like an active area of research. So for example, that's not what everyone says, but there's, you know, it's quite popular now to talk about loss of plasticity and sort of plasticity. For anyone who heard those keywords, it's a big topic, particularly in RL. Claire Lyle and co-authors in this paper are basically arguing that plasticity loss is just another name of like vanishing signal. I mean, it's basically the same mechanism. So plasticity is about, if I train on task A and then I switch to fine tune on task B, sometimes my model just not learns task B. You know, like the model just doesn't want to learn anymore. And they call this loss of plasticity. And what happens in this kind of scenarios? Well, 99.9% of the times, all it happens is when you start fine-tuning on task B, your gradients are vanishing for various reasons. Either your activations are saturated, or there's some pathology in the Jacobians, and you get sort of this very skewed Hessian or whatnot. You know, like pick your choice. There's a lot of weird behaviors that you can have in optimization, but they all come from this chain rule. Like they're all coming from like how the Jacobians behave. Like if one of the Jacobians behave weirdly, that they're going to mess up your gradients and you're going to mess up your learning. So it's always useful to look at the structure of your network and to understand how signal propagates. And you know, we had papers about LLMs about that, and you know, it's still like very valid way of understanding neural networks. So it's quite useful. The other question that you can ask is, how do I decide this trust region? So, and I'm not going to go into this, but this is sort of all the space of like improving optimizer for neural networks, Adam, and all of this. This is all it is about. It's like, if I have this loss and I have this gradient, how do I make the right choice of the step size? How do I make this thing converge as fast as possible? You know, there's different ways. So if you do some sloppy math, you can kind of see that a quantity that tells you what would be the right step is the Hessian, because it tells you how quickly my gradient is changing. So if you have that intuition that you're saying, well, I did this approximation and now I'm going to move in this direction, you can ask yourself, well, how soon would this direction change? If I would recompute my linearization, when would this direction become something different? So you want to look at the change in your gradient. And if you measure your change in the gradient, well, that's just a Hessian. The Hessian is sort of how quickly your gradient is changing. So therefore, the Hessian tells you something about the step size. The other thing is, and a lot of people do this, this looks a lot like a physical system, right? It's like a surface, I put a ball in and I let it roll. So there is a lot of intuitions from physics as well. Things like momentum and so forth are basically just straightforward taking intuitions from physics and adding them here and trying to use them. So yeah, I just wanted to give you that, you have the basic algorithm that is going to work, and then you have all of these changes. And I think for brevity, I've removed slides on atoms and stuff, but atom is just a particular, you can think of atom as just not using the Hessian, but using a different matrix. So they use like empirical Fisher, which is, you can prove that it strongly correlates with the Hessian in certain instances. And that's kind of the intuition. So you take some kind of matrix that tells you the rate of change, and then you approximate it. And in Adam, you approximate it by a diagonal, because anything else would be expensive. So if you want to get, Adam basically takes the gradient and divides it by gradient squared. So you have this matrix, which is diagonal, which has on the diagonal the gradient squared, and you do 1 minus that because you're dividing by it. And that is just sort of a way of measuring how quickly the gradients are changing. And you can show that mathematically. So there is an equivalence between Fisher information matrix and Hessians for supervised learning and so forth. So I'm not going to go in any of those, and maybe that doesn't mean much to you, but I'm just sort of saying that this sort of overall framing is generally enough that it kind of fits most of the work that's happening right now in optimization. But obviously it's not about optimization, right? We care about generalization. And this is how people were thinking about this, right? Like if you say, well, this function is nonlinear and I have this local process that keeps going, and what is this process going to do? It's going to converge to the closest minima that it sees. And if I have some ugly surface like this or that, like what hope is there to do anything interesting? Like basically initialization would be as important as anything else, because that will define where I'm going. And wasn't actually any answer to this. Like everyone said, yeah, that's how it is. And then the only reason the field moved on is because there are some people who are like, yeah, this looks bad, but maybe it's not that bad. Let's just do it, right? So deep learning really moved forward because of empirical results. Like there was no theory that was telling that you can do anything. Like no one even tried to do anything on the theory side. They were like, let's just run it. And they ran it, and it worked really well. And they're like, you see, it works. And that's it. And many people had those results, and it kind of went forward. But like things change, right? So this was the early days. Then we went into this other phase, and I think we're still a little bit into it, that I call it the deep learning myth. And Ilya Sutskever actually had a phrase this was back in the day when he was a PhD student. I don't know what he's thinking right now, but he had a phrase that was the church of deep learning, right? So we people doing deep learning, we were part of the church of deep learning, and that's because we believed in deep learning, right? We said, well, deep learning will solve this. Like, we don't know why. The theory says it shouldn't, but it does, and we believe in it. And there was this sense that even when you had like a student to work with, if the student did not believe, then things would not work out, the experiments would be bad. If the student believed that this would work, then things would work out. So you'd look for the students who would believe that the networks just magically do things. But really the myth is that optimization is as if everything is convex. There's nothing weird about it. And there are some reasons for it. Some of it are very deep. So there's this works in physics that are kind of claiming that as you scale things up, there's something magical happening where you start getting a strong correlation between the index of your critical point and the error. The index is the number of, I'm going to mess this up, but it's the number of negative eigenvalues that you have for the Hessian when you get to that critical point. So if it's a minimum, you shouldn't have any negative eigenvalues. So that's a minimum, like all eigenvalues are positive. If you have negative eigenvalues, then this is a saddle, it's not a minimum. So why is that important? That's important because gradient descent can, in theory, escape saddles. They might need a lot of time because they might be stuck in some plateau. But in theory, there's always a descent direction. There's always a signal that you can follow to get out of it. So this kind of theories that were kind of empirically checked on neural networks is saying that as you make the model bigger, you'll always have a descent direction. Because if it's not a global minimum, then because of this correlation between the index and the error, then it has to be a saddle. Like you don't have bad local minima, you just have lots of saddles. This was the hypothesis. And then there's a lot of empirical work that are kind of trying to justify this. So there's a period in time where you'd get all of these papers that were doing different kinds of experimentation to show this. So Oriol and Ian Goodfellow had works on this. This paper here with Jan de Fan, I was involved in. And all of these are just trying to say that, yeah, as you scale things up, optimization becomes convex. And this is sort of like where the myth kind of started, that you should not worry about it. This is obviously not true. It's kind of nice. You can do theory, but you can also prove that the theory is completely wrong. So we had this really nice paper with Ocek. This was much later. It was sort of his idea. Like Ocek is he's very out of the box thinking kind of person. I really loved working with him. I hope to work with him more. So he wanted to say you know what? I'm going to prove that if you give me a random picture, and here we have a Christmas tree, I can find a place in the loss surface where the loss looks exactly like that picture. And this paper is actually a theoretical paper that shows that for any shape you give me, I can find the shape in the loss surface. So that means that I can find whatever kind of structure I want in the loss. If I want to find a local minima, I can find it. And then we started doing all these kind of simulations where we had an MLP learning on MNIST, and we're looking for Christmas tree. And this was around Christmas, so all of the pictures were Christmas tree involved. So you can definitely show that there are bad local minima, and that number doesn't disappear. It might disappear in the limit at infinity, but for any finite model, you can prove that they have a lot of local minimas that they cannot be reduced. And there's trivial ways of constructing that. So for example, you saturate all your units and then there's no signal flowing. So obviously that model is not going to learn anything. And there are fancier ways of building those. And this is another proof that a local minima exists and you can't get rid of them. And just to contextualize these two works, basically I feel what's happening is that because of the initialization we used, there is a region around the initialization where learning is well behaved. And this is where the myth about deep learning is. But the problem is, as soon as you move away from that region, things become very ill behaved. So that's why you have these both regimes. And what happens in a lot of these works is that actually we're not necessarily staying close to zero to find these regions that are ill behaved. And now the question is it sufficient to stay close to zero? And how close to zero do you have to stay for learning to be well behaved? This is something not necessarily that we understand well, but I just sort of wanted to contextualize this because usually in deep learning, I have no idea how I'm saying with time, but usually in deep learning, people like to be very drastic, right? They will be like, we solved this and we solved that. And you'll find a lot of papers that contradict each other. And this is because somehow we got into this tendency of making everything black and white. But there's always almost for any result that you have in deep learning, you can always find a paper that says exactly the opposite. And somehow neither of the papers are wrong. Somehow they're both right. And you just have to navigate that and understand what are the hidden assumptions that they're making that they make them be able to say this, and what are the assumptions these other guys are making that allows them. So this comes back, for example, we are discussing our LLM steering complete, and you find papers that say yes, you find papers that say no, and they're all from reputable sources, and they're all very technical, and it's the same thing, they're just not talking about the same object. They're making slightly different assumptions and then leads to very different conclusions, and this is kind of what's happening here as well. The biggest issue is these papers were really not explicit about what assumptions they were making. And I'm saying this as a co-author of one of these papers, right? We're just kind of make it sound as, yeah, everything is fine. Okay, so let's see if I get to talk a little bit about generalization as well. So we've talked a lot about optimization, but then it's about generalization. And then this is the usual example, so it's kind of a textbook thing, is okay, if I have these data points, what is the right fitting? Is it this line? Is it this one? Or is it this one? And we always say, well, the order 9 fit is not the correct one, right? Because it looks ugly. But then what does it mean to be the correct one? And this is where generalization comes in. So really I mean, there's different ways of introducing this, and I'm not going to be very formal or doing very well here. But really, like when it comes to generalization, what we do is we're taking sort of the statistical view of everything. We're assuming the data is IID sample from some distribution, and because of that, then we can start making some basically some headway in explaining sort of how to deal with that. And the way we do this is by using this sort of independent validation set or test set. And because it's independent, then it's going to give us a clear signal of how you're going to behave on data that you've not seen. And also from the probabilistic view, you start having this sort of simplicity bias, and you understand that you actually have a prior, and that prior is that the simpler the model, the better it's going to generalize. That's going to be affecting things. So just to make things a bit interesting, so this is the default. So this ID assumption is everything in deep learning at the moment. I do believe we're getting to a point where the ID assumption, we can't really preserve it. Like for LLMs, because of scale, it's not clear to me we're doing ID things anymore. And it's an interesting question of what happens when this ID assumption is not true anymore. Like, what can you actually say about the systems? And I feel like this is one of the next big things, right? Like trying to understand how can we get rid of this ID assumption, and then how do we evaluate systems? How do we do anything at that kind of point? It's a hard question. I liked, so you have folks like Marcus Hutter and so forth, that I really like sort of this frequential minimum description length perspective, and I'm not going to talk about it, but this is an alternative. So like in in this frequential learning, frequential evaluation regimes, you're not making a statistical assumption anymore. You're making other assumptions. So that's usually the life. You can't really have something without assumptions. So there's different assumptions, but there's no assumption that there is a fixed distribution you're sampling from. And therefore, there's no assumption of ID-ness or anything like that. And I find that quite interesting, and I think these works are kind of interesting. Again, like if you read these papers, at least sort of the more deep learning-y oriented one, they make it sound like magic. They make it sound like we don't make a statistical assumption, we make no assumption, and it works. And I think that's not true either. They're making some assumption, and actually it's a bit tricky because understanding what that assumption is hard, because we don't have the mathematical tools sharp enough for us to be able to talk about it easily. And I'm pretty sure that someone like Marcus Hutter or Jürgen or others who are very keen on this minimum description length, they understand what the assumption is, but I would imagine average person does not understand what is the assumption that frequential learning is doing. But implicitly, I think we are now in an era where we're kind of implicitly using something like frequential learning, because definitely when we're training LLMs, we're not doing this in an IID fashion anymore. Okay, so what is the traditional view of learning and generalization? So the idea is we have this test-train separation, you run things, and the theory, the statistical learning theory would say that the train and test would correlate, and as the training goes down, the test will go down as well. And then you're gonna have these three phases, right? One is when you're underfitting, so training is going down and your test set is going down. You have the space where you have a good model. So that's sort of like where you're kind of plateauing. And then after that, the training will keep down, but then you're going to start overfitting. And the intuition is you have in your data noise. As you're training, as you're optimizing, going for zero error, the training loss is going to try to fit the noise that you have in your training set. And that noise is not informative about your test set. And therefore, your test set is going to go, it's going to become larger. And what is the high-level traditional view on this? How do you fix this? Well, you fix this by controlling the capacity of your model. Because if your model does not have enough capacity to model this noise, then it's not going to do it, right? So in a traditional view, the plan was what you have to do is you have to find the right size of the model. When you're training these things, you have this continuum and you need to find it. And this continuum is basically in terms of the model size, right? We know that expressivity-wise, the bigger you make the model, the more capacity it has, the more it can represent. So, you don't want models that are too large because they will overfit any noise, and you don't want models too small because they cannot fit your function. They're not interesting enough. And you can control this by controlling the size, the capacity, or you can control this by regularization. And you can think of regularization as by saying, well, you have to learn something else as well. So now you have to waste capacity to learn that something else. Or you simply, like if you want from a loss point of view, you have some simple, on this, is it? I don't know if it's working, but you have the simple regularization L2. So, this has a minima 0. It's a very simple, like, loss surface. I have some random one, and you just superimpose this. And basically what this will do is you're gonna make the minimas of this complex surface that are closer to 0 to be lower than the minimas that are not. So, you're creating like an ordering between them. You're creating a prioritization where you're saying, I'm going to prefer the minimas that are closer to 0. And that's sort of your prior, that's your regularizer, and that's another way of dealing with the noise. That's another way of limiting what you can learn by minimizing this. It's also useful to understand, and most people know this, but sometimes some people don't. The optimizer itself is regularizing learning. One way it does that is through a number of steps, right? It's very trivial. Like if you're thinking, okay, I have a universal approximator, I can approximate any function. But if I'm allowing myself to only do 5 SGD steps, then there's going to be a much smaller set of functions I can represent, because there is a smaller set of functions that are 5 SGD steps away from where I started, right? So by just the number of steps that you're doing, you're limiting how far in the space you can travel, your minimum the maximal distance, and this is again like sort of reducing what you can represent, right? So so the optimizer is doing that for you. And I think, yeah, what I wanted to do this slide is a bit like overwhelming, but what this slide is trying to say is that, so I guess maybe you guys have noticed that nowadays people are saying, like all of this work seems to say that the choice of architecture is important, because the choice of architecture tells you about the shape of, in this space, the shape, like which functions you can express, right? And then you had regularizers to further restrict that, but like all of this story keeps sounding like if you pick the right search space to look for your function, then you're fine, because that search space will only include functions that are good. And that's what we're doing. We're basically kind of shaping that search space with the regularizer, with the number of steps we're doing, with the size of the model, and so forth. So we only have like a good search space to look into. And it makes it sound like it's a lot about sort of architectures and how you limit their expressivity and so forth. But nowadays, like there is a trend where people are saying that we don't need to worry about architectures anymore. Transformer is all we need and whatnot. And there is this sort of data-centric view on machine learning. And we have like workshops and so forth that are talking that in this new era of machine learning, we should not think about architecture design. We should not think about optimizers. We shouldn't think of any of this. It's always the same pipeline. The one thing we should think about is what is the data? And that's the only thing we want to optimize. And I just wanted to, like this slide is meant to explain why we got here and what is this whole data-centric view about. Obviously, this is driven by empirical observation. For these big models, it turns out that if you want to impact their behavior, the easiest way to do that is by playing with the data. You get a lot more out of it than if you just try to add some changes to your architecture design. So why is that the case? And I think the reason we got here is, well, first of all, is because we're wasting a lot of compute. But we got here because we have these big models and we have enough compute that other things are not becoming limiting as much as before. And it's because, and this is sort of what this little drawing here, this kind of weird rabbit is trying to show, is because basically everything that you do when you're trying to train a model, when you're trying to create a model, it's limiting or introducing inductive biases in the model, right? So we used to think in terms of like how people would usually present this would be just sort of this outer shape, right? You say like, oh, I pick a family of function H, and this defines some region in my functional space, and this is what I restricted my search space to, right? I can only model functions that can be represented by H. But the truth is, for neural networks, because they're nonlinear, you also pick an initialization, and the initialization limits what functions you're going to be able to reach. So it's not just H, it's the initialization itself that is telling you, no, you only have access to this small subset. And then there is the optimizer and the number of steps that you do. That again limits the space. And then there is the data. So basically, the data does that as well. And I think the reason we're in this data-centric view is becoming popular is because the function h is generic enough that covers a big chunk of the space, such that you're, instead of worrying about the space of function you can represent h, it's better to worry about the reachable h, which is the set of functions you can reach by doing learning the way we're doing on this data. And actually, in the past, this reachable set used to be very close to h, so you would not think of it, you'd only think of h, and you say, you know, if I fix h, I implicitly, I mean, this reachable set is always within h, right? It can't go outside. It can only be inside h. So before, h used to be the main factor. H was so small that it couldn't do what we wanted, so the main thing you had to do was to make h bigger. But now we got to a point where the walls we're hitting is more about this reachable h, and it's actually more useful to think about this many times. There are situations, and I'm not going to get to talk about it, where h is just insufficient, it can't express certain things, but yeah. Just trying to drive this message home is that anything that you can do can change things. I just sort of wanted to make this observation, and because I feel like a lot of people don't usually think of it this way. So people, when they think of regularizer, it's always a term that you add. But I'm just trying to say that it's not just that. Everything is a regularizer, like the optimizer as well. So particularly, for example, the choice of optimizer, well, now it's a bit louder. The choice of optimizer that you have can change the distance between points in the space, because the optimizer describes how you're traversing the space. So changing the optimizer, it's almost like changing the metric of the space, right? It can contract space, it can expand space in kind of interesting ways. So you can have the situation that you're here, where, you know, this is like two minimas, your initialization starting point is there, and this is the kind of how long it will take HGD to go from I to O1 or to O2, and usually you know that HGD goes to the closest thing that it can see. But if you change the optimizer, you can magically make the distance between I and O2 much, much longer, because now the optimizer takes a very weird path in the parameter space. So you can change which minima you're going to converge to by just changing how you're traversing the space, without necessarily changing, you know, the value of your minimas or anything like that. So I don't know if this is clear, but I'm just sort of trying to get this point across, that I think we're not acknowledging that basically everything we're touching is an inductive bias for a neural network. There used to be, I don't know, I guess not many of you were around the early days of deep learning, but the deep learning revolution was all about, we're getting rid of all inductive biases, right? Everything is learned from the data. We're not prescribing anything to the model. That was the philosophy. That is not true. There's no such thing as I'm just learning from the data. Anything that you do will restrict the search space in some way, and it's going to be imprinted in the model. And particularly in neural networks. In neural networks, you can take a model, and from it, you can figure out what was the initialization. Because it's not like a process where the initialization disappears and you're converging to the same point. This is a nonlinear function. You have many minimas, so you can read out from where you converged. You can read out where you started. So everything that you've done to that model, the choice of optimizer and so forth, they're still part of your solution, right? They're shaping your solution. It's not some magic where it's like, these are just, they make learning easy, but they're going to be vanished by the end, by the convergence. That's not what's happening. Everything is an inductive bias, and I just wanted to shape that up. And this is kind of saying the same thing. This is not a convex space where, like, no matter if I start where I start or what optimizer I use, I always converge to the same point. Like the choice of optimizer, the choice of initialization, and so forth means I'm converging somewhere else. And I think that's kind of interesting. And this is sort of also like, like I was saying, the traditional view is you need to be careful how big you make your model so that you don't overfit. So nowadays, we don't do that, obviously, right? We make the model as big as we can. Like no one is worrying, would I overfit? Like, they're just asking, can I make it bigger? So why is that? And like one answer is from this paper from Misha Belkin, which is really cool. It's sort of idea of double descent that everyone probably has heard of. And I'm just going to give you the intuition. So as you blow up the model, you get more and more minimas. Therefore, you have the ability to fit any noise you want. I mean, that's the idea. You get so much expressivity, you can fit anything that you want. But because you're using gradient descent and some form of it, what you're going to do is you're going to converge to the minima that's closest to where you started. Because SGD is lazy. SGD does not like to travel a lot. So SGD will just go to what is closest to you. And what Michal Belkin is saying in this work is that as you're growing the model, as this sort of number of minima explodes, you're going to start having more and more minima close to where you start. And these minimas are getting closer and closer to you because they're becoming so many of them that they have to get closer to you, right? It's sort of just some like magic of density and other stuff and math and high dimensional spaces. But like lots of these minimas are starting to get closer to you. Therefore, you're going to converge to something that's close to initialization. You've initialized a model close to 0, so you're going to converge to something that's close to 0. So therefore, Occam's razor, this is sort of a very generic function because it has very small weights, it's very smooth and whatnot. So this tendency of neural networks to find smooth functions, to find small norm functions and so forth is just sort of side effect of HGD because HGD does not like to travel far. So that's why increasing the capacity doesn't hurt. It actually helps. And the reason it helps is because it acts as a regularizer. The way it acts as a regularizer is because it pushes minimas closer to 0. So you're more likely to find them. So you're more likely to find a small norm solution. And you do this without adding like an L2 penalty on your weights, which acts in a weird way and doesn't have the same effect. So I don't know if that's clear, but this is kind of the high level intuition behind double descent. Okay, so this is almost like a side story, but it's just sort of something I like a lot, so I'm going to mention it. So there is a lot more to. It's important how you get to your solutions. This is sort of the importance of IID assumption and what happens. And I just sort of wanted to say that like the way learning is happening in neural networks is actually quite awkward. And once you start thinking about it, it's exactly the opposite how you would learn. I think people sometimes like to make parallel between artificial intelligence and humans and whatnot. So the learning schemes are completely different. So in particular, the way learning happens in deep neural networks is through this tension that happens between gradients. So how do you learn? Like you have a bunch of examples in your batch. Each example has a gradient, and then you're averaging the gradients. And you can interpret this as each gradient is looking at the weights, and they're saying, I want to increase this weight, or I want to decrease this weight. And when you average them, it's like they're voting, right? So what this does is create sort of this tug of war dynamics where some examples are saying, I want this weight to go here. The other example saying, I want it to go in the other place. And convergence happens when you reach an equilibrium between sort of this tug of war kind of dynamics on the different weights between different examples. So why is this important? This is important because you can ask yourself, what happens if I remove one of these guys in the tug of war game, right? If I take some data away. Well, it's obvious the other guy is going to just pull the rope all the way to themselves, right? There is no force to stop them. And this is sort of the basis of catastrophic forgetting, right? So how do you, basically you cannot, as soon as you stop seeing an object, you're going to forget about it. That is the problem. Because as soon as you stop seeing that object, there's no more any force that it's forcing your weights to preserve the knowledge that you had about the object. You need that constant force because there is always need to be this tug of war. Like you can't, humans learn in a very incremental way, right? You learn the basics of math and then you go to more complicated math and so forth. Like you can't just, I'm going to first do derivatives and then go back and learn about addition. You're learning you're building up knowledge. You're learning in a constructive way where your knowledge is based on the information you have before. Neural networks can't learn that way. Because if you start learning how to compute derivatives and you don't have addition in your training data anymore, there's not going to be a guy to pull on the weights to say, wait, I was using this to represent how to add numbers. So you're going to forget it. And this is, I think, it's quite interesting. And it leads to very weird dynamics. I'm not going to go super deep into this, but just It's this kind of weird thing. So we're doing experiments where you're trying to learn multiple things at the same time. So this is a thought experiment. We haven't actually run this experiment, but imagine you're trying to learn an agent to play with Zorg and to play with Protoss. These are different races in StarCraft. This was around when we was doing Alpha Star, so it was all about StarCraft. So this is just learning two different tasks. One is to play a game with Borg, the other with. So to learn this, you have to show them both at the same time, because otherwise, as I was describing before, it's not going to work. But then you look at how you learn this task, and it turns out that you're not learning both of them at the same time. What happens is you learn one of them, and then you learn the other. And this again is because of weird dynamics with the gradients. So the issue is, if some gradients are larger, they're going to dominate learning, and they're going to take over, and they're going to prevent the other tasks to learn. Basically, as they learn more, their signal becomes stronger, and they keep punishing the other task and say, like, you're not going to learn now. And it's only when they're getting close to convergence that gradients are going to start vanishing, and then the other task has a chance to learn. So you're learning things sequentially. But because of the forgetting, you can't, after you've learned how to play with Zerg, say that's the one that takes over, you can't say, oh, now I can throw this away and just learn to play Protoss, because you start forgetting, right? So you have to still presenting all games. And which of these tasks is going to dominate, you don't know before, right? You can't predict, oh, I have this task, this is going to be the one that learns fast. This is just sort of like weird stuff based on initialization, random numbers, and so forth. So it's kind of weird. So basically, I'm just saying this is because if you're like, I use this to motivate why deep learning is so wasteful computationally and data and everything. Because you think of it like anything you might learn is composed, you can decompose it in subtasks and all this stuff, right? And if you're not learning all of these things at the same time, but you're learning them sequentially, then you're wasting a lot of compute looking at things that you're not actually learning, because you're sampling IID, you're looking at everything at the same time, but you're learning them one at a time. And because of this kind of tug-of-war dynamics, you can't throw away and just say, oh, I'm going to learn A first, and then B, and then C, and D, and be very efficient computationally and very efficient data and so forth. Because if you do that, you're going to forget everything. So I'm just basically saying that the dynamics of learning, this issue of us not being able to do continual learning, is potentially the reason why deep learning is so slow. And solving this credit assignment better, making it so that you can learn in an incremental way, you could become super data efficient. You could say, I don't need my LLM to see like trillions of tokens or whatnot, whatever, something that a human cannot see in their lifetime, or whatever the latest catchy thing is. I can learn in a data efficient way. And yeah, I just wanted to say we actually have a conference on this, and maybe the only reason I'm bringing it up is because, the conference is going to be in Romania next year, so it's close by if you guys want to come. And it's a conference about how do we get rid of the ID assumption, and what happens once you get rid of it. I have 5 minutes. Let me just jump through some stuff. So I wanted to motivate why structure is important. And I wanted to use that to introduce transformers. I don't think I'm going to have a lot of time to introduce transformers, but I'm just going to go with a few slides for you, at least to understand where the tension is coming from. So I just wanted to say that a lot of sequential models were developed in the context of natural language modeling. And in natural language modeling, all you're doing is you have a sequence, and you use the probability chain rule to write it like this. And then the question is, how do you approximate these quantities? And there are two things that usually happen. One is, for many models, you need to make this nth order Markov assumption. So you need to cut the sequence. Instead of going from 1 to t minus 1, you pick some t minus n, because that would give you sort of a format to the input that you can handle. And the second thing is you need to pick f. And a lot of thinking in the sequential model was around this n-order Markov assumption. Is it okay for me to cut the sequence and say, my next token is just a function of my previous 3 tokens? Are they enough to predict what's going to come next? And usually people will say, no, that shouldn't be the case, right? And initially, we had to do this for necessity, and early language models were all about like using MLPs or convnets. But there was an answer. There was recurrent neural networks. That didn't work. And transformers are meant to replace recurrent neural networks in the sense that they're trying to answer this. But I don't have time to go into that. I'm arguing that they're not. And actually, there is more and more work that are trying to say that, well, this nth order Markov assumption is not that big of a problem, if that n is pretty large. Um, I'm just presenting this because there was this sort of lot of focus at some point to try to get LSTMs and all of these recurrent models to be the thing, right? And then we also even had some like early examples, like we had the WaveNet kind of architectures where Null and colleagues were like basically introduced this nth order assumption, and they said, well, it's not really about that. It's just about what scales better. And then that's basically the story with transformers. Like transformers are the main tool, not because they model that distribution better, I would argue, is because they are scalable a lot more, or at least that's been sort of one of the main thinking in the field, is that kind of going back to the things we were discussing before, we sometimes worry a lot about expressivity and what is the right class of models, but sometimes it's not about that. It's about what is easier to learn, what runs faster, and that's what's going to, even if you know it's the wrong architecture, even if you can prove that it cannot express what you're meant to learn, because it's cheaper and because it learns better, it's going to perform better. And there's just sort of a message that I think it's important and to people to be aware, because sometimes you get stuck in this, like, I need to have the right architecture, and it's really not about that a lot of times. And with that, I think I'm gonna stop because I'm probably out of time. And if there's any questions, thank you.
Thank you, Razvan, for such an inspiring start to the day. We have time for maybe one or two questions. So, if anyone, yeah.
Hello, thank you so much for your presentation. So I have the question regarding the model's expressivity. Yeah. Do you think if there's like a measurable trade-off between the model's network's expressivity and the inductive bias? Something like, I don't know, the surface where increasing one decreases the others, because I'm not aware of any universal closed form of this like trade-off surface. Thank you.
Yeah, I don't think I don't know of any work that's framed like this, but I think you can't also frame it as generic as you said. Like it probably needs to be very specific. Like you need to pick an inductive bias and you say, okay, how well aligns to this. But still, I haven't seen anything like that either. I mean, I believe, and this usually happens for just, it makes math easy. Expressivity works usually kind of ignores everything else and simplifies things, and then they can come up with very nice, like tight answers. What I think should be the future of the theory side in that space is really maybe things like you said, and things like what is the relationship between expressivity and learnability. But I feel like, just taking at least two dimensions into account at the same time is something I haven't seen, and I would love to see. Like we don't even have a lot of results in about sort of speed of like how quickly, so like we know it's a universal approximator, but like how quickly are you approaching that as you're increasing n, like we have for convergence, like some rate of expressivity. I don't even know works like that, which to me would feel quite important. Or like we know that both MLP and ConvNets are universal approximator, but if I have a fixed size for the MLP, what size for a ConvNet do I need to be able to express that MLP? We don't have that either. Like I think this kind of stuff would be really cool.
Thank you.
So there's this thing I was reading on like superposition in neural networks, that like neural networks somehow encode more dimensions than they have features. For example, mapping 5 different dimensions in a 2-dimensional space. How true is this? Is this a real thing? And what are your opinions on this? Is this the reason why neural networks can express more?
They can definitely do that, and they do that in practice sometimes. So I'm no expert necessarily in this space. So I can tell you the kind of experiments that I know of that we worked with. So for example, you can see that the softmax, like we were doing some experiments where we were trying to understand the behavior of softmax in learning. And softmax has this weird behavior where what you can do is you can increase the rank of the features that you get. You know, you can feed in some low rank features, and because of the nonlinearity, the softmax increases the rank on the outside. And if you play with the temperature, if the temperature is not just right for softmax when you learn, what happens is that the dynamics of learning will converge to a solution where the logits that go in the softmax are super low rank, and most of the rank is recovered through softmax. And it does exactly what you said. Like, you can see this in practice, right? You have n-way classification problems, so you need n, you know, to have rank n to be able to do that, and you have the features that are rank 1 or 2. And then from those 2 dimensions, they reconstruct the whole n. Usually, whenever I've seen this, it also correlates with models that don't generalize well and they behave poorly in practice. And I think there's just sort of something about trying to encode multiple things on one dimension means that you have a very complicated decoding function there, and that usually correlates with bad behavior for the model. So in general, I think large models that behave well in practice probably do not have a lot of that in them, but that definitely naturally happens in learning a lot. And yeah.
Thank you, Razvan.